So we'll begin to study our second family of polar functions called Limacons. And like the previous example, we'll do this by sketching a particular graph. In this case, this is going to be r is equal to 3 plus 3 sine theta. Unlike the previous example, what we'll do first is we'll sketch the graph of r is equal to 3 plus 3 sine theta in rectangular coordinates, and then we'll use this graph to think of it as a table of points. And we'll study how the radius is changing in polar coordinates as we change our values of theta. So starting off again, let's go ahead and sketch our graph. And we're going to be looking at all the values between 0 and 2 pi. Furthermore, let's specify the points pi divided by 2, pi, and 3 pi divided by 2. Now this trig function has an amplitude of 3, and it has a vertical shift by 3 units. So assuming this is our theta and this is our radius, the graph of our function should look like the following. Let me go ahead and reiterate that this is a graph of our polar function again in rectangular coordinates. We haven't yet graphed this in polar coordinates. Let's go ahead and copy this to a new page, and we'll go ahead and notice some general patterns to this graph though. Let's first go ahead and make a table of values of r and theta. So we're given the theta values 0, pi divided by 2, pi, 3 pi divided by 2, and 2 pi. The corresponding r values are given by 3, 6, 3, 0, and 3. And so this is going to break our graph up into the following pieces here. Now we're going to use these pieces to sketch a picture of our graph in polar coordinates. So let's go ahead and draw a second coordinate chart. And this coordinate system again is in polar coordinates. And first we're going to graph the point 3, 0. So our angle is given by 0, it has distance 3. And now graphing our second point here, 6 pi divided by 2. So now again our angle is pi divided by 2. And so we'll get a point approximately over here. And the thing we want to notice is that as our angle increases from 0 to pi divided by 2, then our radius is increasing. So we'll get a line that looks approximately like this. And we'll be using this idea to graph the rest of our function. So let's go ahead and graph the remaining points. We have 3 pi, which is given by this point here. We have the point 3 pi divided by 2, 0, which is this point here. And our final point is going to be given by 2 pi, comma 3. So we end up back over here. So as our angle pi increases from pi divided by 2 to pi, our radius is decreasing from 6 to 3. And now, as we increase our angle from pi to 3 pi divided by 2, again, in this region here, our r is going to also be decreasing from 3 to 0. Then, from 3 pi divided by 2 to 2 pi, again, our r increases from 0 to 3. So our graph in polar coordinates will look approximately like this graph over here. The graph in this problem is called a cardioid because it's heart-shaped, and it's a specific example of a limacon. Let's go ahead and introduce the other types of limacon graphs. There's two types of general equations given by r is equal to a plus or minus b sine theta and r is equal to a plus or minus b cosine theta. In both instances, we have that a is greater than 0 and b is greater than 0. And we have 4 types of limacons. We'll start with the previous one, a cardioid. And this occurs when we have that our a value is equal to b. And again, this is roughly a heart shape. Let me go ahead and try and redraw that a little better. Now, if we have our a value is greater than b, then what happens is this dimple is pushed out. So our graph would look something more like this. And this is called a dimpled limacon. In the other case, if we have that a is less than b, then what happens is we create a loop. And this is just called the limacon with an inner loop. And finally, the last case is when our a value is less than or equal to 2b, then we further push out our dimple, so it looks like it's almost a circle. So one way to think about this family of polar functions is that as our a value is getting larger, we're really pushing this loop out further and further until we get to the point where our limacon more or less looks like a circle.